Okay, so again, thank you very much for putting on this conference. I'm really sad that I could not be there, but there are just too many conferences this year. So I'm really happy that you could make it happen in person. And I wish I was there. Okay, so I'm talking about hopefully not just hydrogen sulfur containing compounds, but maybe we'll get to move on to other compounds too. I don't want to go too much into background since most of us are quite aware of the research that has been going on in this very quickly evolving field. Here I just show that there have been a number of superconductors that have been reported with very high TCs approaching room temperature under high pressure. This plot is old and it does not encompass all of the new experimental developments that have happened in the last year or so. And that when you take a look just at the binary superconductors, there are more or less two classes that have high TC. One in this sulfur hydrogen type region that is embodied by this H3 S phase. So these are what I would refer to as P block hydrides, and the other types of systems that are very different in the sense that they contain these types of superhydride type cages mixed with an electropositive element, and this lanthanum H10 system is just one example of ones that have been synthesized. So hopefully I'll be able to talk about ternaries of both sets of compounds within my talk. Okay, as we all know, there have been really recent exciting reports of room temperature superconductivity in high carbonaceous sulfur hydride. However, the problem is we don't really know what the phase is, and we would all be really excited to figure out what this structure is and understand its superconducting properties better. So there was research published by Russ Hemley, Ranga Diaz, Yangfang Gi, that noted that there is this peak in the density of states near the Fermi level in the pure H3S. And if we could then just move the Fermi level to lie right on top of this peak, we would be able to increase the superconducting critical temperature of H3S. And this could be then accomplished by doping, for example, by carbon of about 3.8%. And there were calculations done with the virtual crystal approximation that found TCs that were really quite in line with the experiments. So we wanted to take it to the next stage, going beyond the virtual crystal approximation and actually introducing carbon atoms into the system to see how this would perturb potentially the bonds within the lattice, and then afterwards affect the superconducting critical temperatures. So we took a look at different ways that one could dope H3S with carbon. This is one structure that I showed right here, where you have a carbon atom that is going to be octahedrally coordinated by hydrogen atoms. And here's the electron localization function of this atom, showing that you indeed have these types of strong carbon hydrogen bonds, as well as these more multi-centered SHS bonds. And what we note that is quite interesting is that if you look at chemistry at 1 atmosphere, especially molecular chemistry, there is a wide variety that has been done on carbocations. So those are ions with carbon containing a positive charge, in particular by George Olah, who was awarded the Nobel Prize for this research. And we do not see that carbon assumes an octahedral coordination. Rather, it has this type of a C2V symmetry with two sets of shorter bonds, the two-centered two electron bonds, and two longer bonds where you have two electron three-center bonds. So this would be the species that would be stable in molecular chemistry. And what we find is that under pressure, this octahedral coordination can be found, but only at very high pressures. If you decrease the pressure, it becomes dynamically unstable, and also only for very low dopings of carbon. If you have higher carbon dopings, the octahedral environment is not favored. And indeed, according to a Bader analysis, you do see that this CH6 does become positively charged, a slight positive positive charge in the calculations. We do find that there are, however, weak interactions between the hydrogen and the sulfur, not enough to form any kind of covalent bond, but there is some sort of a steric interaction that is keeping this octahedral coordination from stable at the very high pressures. Next, we turned to a tetrahedrally. I put this in brackets because this CH4 is really no longer tetrahedral geometry. It is a 4-coordinate geometry. And we find the situation has changed in some ways. First of all, the CH4 is more or less neutral according to our beta charge analysis. Again, we see this strong carbon hydrogen bonds, and we do not see any kind of bonding really in our electron localization function or using other descriptors such as the crystal orbital Hamilton populations between the hydrogen and the HS lattice. And dynamic stability here is found in a larger range of compounds in terms of the stoichiometry range, and also down to lower pressures, for example, down to 180 gigapascals. So next, if we take a look at what happens to the electronic structure in these systems, we see here on the right-hand side the density of states of H3s. And then what happens when you have these octahedrally or tetrahedrally coordinated systems, the density of states at the Fermi level actually drops quite dramatically. And the reason for this is a few things. First of all, the doping actually breaks degenerate bands near the Fermi level by changing the hydrogen-sulfur bond distances. Note that the carbon-hydrogen states are not at the Fermi level. And also you're localizing these electrons that were previously metallic in these types of covalent type bonds. So we're going to be changing the density of states due to this reason. And so, for example, in H3s, while you might have 14 bands crossing the Fermi level, in the doped phases, you only have 11 bands. There is another type of system that we take a look at, and that is instead of doing a carbon substituting a sulfur, what would happen if you have SH3 substituted by CH4. And so compared to some of the systems that I showed earlier, where you have this type of a geometry, you would basically be adding this one extra hydrogen to your sulfur hydrogen cage. And note that it does not have much of an impact on the DOS at the Fermi level. However, what it does have an impact on is the dynamic stability range. So these types of substitutions are going to be stable along a much larger stoichiometry and also pressure range. And in our calculations, we also considered what would happen if you added one extra hydrogen to the sulfur hydrogen lattice. And at least for the models that we considered, we found the enthalpy of formation as being too positive, and we think that is due to the steric hindrance between the methane and all of these hydrogens attached to sulfur that is just going to increase the volume and not be favorable. However, we do note that adding in this extra hydrogen, actually, because it stretches a number of the sulfur hydrogen bonds, it's going to change the vibrational properties of the lattice substantially. So for example, the Debye temperature of this phase is much higher. So it could still have an impact on TC by not the density of states, but by the vibrational properties. So as noted, thermodynamic stability, all of these phases are not thermodynamically stable, for example, with respect to H3s, but they're really not all that unstable. And we have seen in calculations that, for example, the calcium 2 H5 has been made. It's about 20 MeV per atom off the convex hull. The phosphorus hydrides have been made. There, if you look at the calculations, about 40 MeV per atom above the convex hull. And note that these calculations are done at 0 Kelvin, whereas the experiments are done at very different pressures, oftentimes with laser heating or with photochemical heating. So it's not impossible that some of these types of hydrogen, these types of carbon dopings could potentially be made, given especially the fact that if you look at the low doped phases, they are really very close in energy or in enthalpy to the H3S phase. But generally speaking, the SH3 substituted by CH4 is the most stable. The 4 coordinate carbon is the second most stable, and the octahedral coordinated carbon is the least stable. And note that we are also not considering configurational entropy in our calculations, which could also further favor the introduction of carbon into the system. So we took a look at the superconducting properties using either the modified Macmillan equation or the solution of the Allen-Dynes equations using the Elias-Berg spectral function that was calculated within Quantum Espresso. And we note that none of the phases that we have considered to date are going to be actually reaching the TC of H3S. The best phase that we have found is the R3MC SH7 that was predicted in previous work that in our PRB paper that I did not discuss here. But what I would like to point out is that even though we have gone one step further, then taking a look at the virtual crystal approximation, what we have not considered is the nuclear quantum effects, which could then serve to, smear out that proton between the carbon and the sulfur, thereby potentially raising the density of states at the Fermi level. So that's not considered in our calculations, nor have we looked at the anharmonic effects. So that would be the next step in taking a look at how the doping actually changes the superconducting properties. Next, I would like to mention our work done on doping. And also I should say that there have been other studies, for example, by Hanyu Liu and many other people who have found very, very similar conclusions. So we also then took a look at what would happen if you doped SH3 with phosphorus. And we note that what is different between carbon and sulfur and phosphorus is that the phosphorus radius is much more similar to sulfur than the carbon radius. You can also dope the SH3 with phosphorus because it has a smaller number of electrons. So it's also going to be moving the density of states in the Fermi level in that correct direction. But sulfur and phosphorus can be hypervalent, and phosphorus is often going to assume octahedral coordination. So we would expect that these octahedrally type coordinated systems that I previously discussed, which are not very stable within DFT 0 Kelvin type calculations, would be potentially more preferred. And I would like to point out that there was a previous work done on this system, again, oftentimes using the virtual crystal approximation, sometimes not, but in the cases where the VCA was not employed, typically only one stoichiometry was considered. There was no crystal structure prediction searches that were carried out. So we carried out crystal structure prediction searches between 100 GPa to 200 GPa. This is an example of a convex hull plot that we found. And generally speaking, there were not too many ternary hydrides on the convex hull. However, there were a number of ternary hydrides not too far above it, suggesting that in principle, these could be made provided that the kinetic barriers to decomposition, as Simona just discussed, are not going to be too high. And there were a variety of systems found. Some of them had these these cages, as I just described, which could be thought of as dopings of the H3S by phosphorus. Others had these types of 2D hexagonal units. So here you can see a phosphorus sulfur hydrogen bond in this type of planar type of hexagon. We also had one-dimensional or 2D sheets. Here I show a structure with this type of HS 2D type sheet, and also with 1D type chains. So all of them were found in the structure searches. We then took a look at filtering out the ones that were, potentially had a high density of states at the Fermi level from those that did not, and also taking a look at other considerations such as symmetry. We really can't do EPC calculations on very low symmetric structures in deciding which ones to consider for the superconducting properties. And what I note here's previous work done just on sulfur phosphorus. If we add just one hydrogen to it, you can really raise the TC by an order of magnitude. However, the TC of these systems is not going to be quite large. Again, adding more hydrogen to it is going to increase TC. But the only systems that had a really appreciable TC are those derived from phosphorus dopings into SH3. Here I show the candidate with the highest TC, which in our calculations was found to have a very similar to TC as that of H3S. I show two numbers here. The ones in the parentheses are the solutions to the Eliashberg equations, and the ones without the parentheses are just the Allen-Dines type equation. And here I show the electron localization function, which indicates that you have in this system more of a phosphorus hydrogen sulfur type bond. And indeed, if you look at indicators such as the crystal orbital Hamilton populations, we see that doping with phosphorus actually does not change the strength of the sulfur hydrogen bond as much as doping with carbon did. And that has to do with the ionic sizes, the electron negativities, and also the fact that phosphorus does like to be this octahedrally coordinated. And if we look at the density of states at the Fermi level for 12.5% dopings of phosphorus, again, you do not see this type of reduction that we saw in our previous calculations on the carbon doping. So we think that phosphorus doping and potentially doping with other elements that are similar properties to phosphorus could also be very beneficial in exploration in these systems. Okay. Next, I'll just mention very briefly that in the sense of ternaries, we also considered what would happen if you mixed something like calcium H6 with sulfur H3. We know that calcium H6 was predicted to have a very high TC. This was recently measured and reported by two different groups. And generally speaking, most of the phases that we found when you mixed like an alkaline earth metal with a sulfur consisted of something like calcium 2 plus S2 minus with a bunch of hydrogen added to it. And these are not going to be high temperature superconductors because they are basically going to be typically insulating. However, we do see some very interesting chemistry going on here. For example, Kupus-like bonding between this H2 that interacts with calcium, where you have sigma to metal D transfer from the H2 and also back donation, and that's going to be modifying this HH distance. There was only really one deviation, and that's this calcium sulfur H3 phase, which was found to lie on the convex hull that we calculated at very high pressure when the 0-point energy was considered. And here I show the phase. What's interesting about it is basically it looks like these types of two-dimensional version of H3S in the sense that you have these honeycomb sheets made up of hydrogen sulfur with this spacer, calcium H2 spacer in between. And we also find that you have this Van Hove singularity near the Fermi level, just like we do in H3S. However, because this is a two-dimensional version instead of a three-dimensional version, we find lower TCs than an H3S, so going up to potentially 100 Kelvin at about 78 or 80 gigapascals. Yeah, this is the TC and this is the pressure at about 130 gigapascals, about potentially up to 100 Kelvin. However, we do propose that this could give rise to a new family of structures where you substitute calcium with another alkaline earth, potentially rare earth, and also you could substitute in selenium or tellurium for sulfur. So turning now to the clathrate superhydrides that have been discussed much in this discussion today. We would like to really understand better why some systems have this MH6 or this MH10 structure, whereas other systems don't. They undergo distortions. And to do that, we decided to use the chemical DFT chemical pressure analysis to look at the internal pressures within these systems. This analysis was made by the Danny Fredrickson group, and till now it has been used primarily to understand deformations and intergrowths and substitutions in complex crystal structures, and also to identify soft phonon modes that could then give rise to some sort of incommensurate modulation. And we thought that this would be a really interesting technique to apply because it also lets us visualize the chemical pressures within the system that goes along with Ashcroft's hypothesis that you could use this type of chemical precompression to add a chemical pressure within the hydrogenic lattices. So just to let you know, this DFT chemical pressure technique, it basically expands and contracts the cell, does a DFT calculation. It then will calculate the pressure using this formula on each voxel point. And after doing a series of transformations, you're able to get these types of maps where I show the white are positive chemical pressures, which means that the lattice would like to expand, and the black are negative chemical pressures, which means that the lattice would like to contract. So let's take a look at the MH6 stoichiometry, which is stable for calcium H6, but it is not for strontium H6. Note that strontium obviously has a larger radius than calcium, and this obviously suggests to us that the reason for it adopting this kind of phase where you have dimerization, so you don't have these hydrogen lattices anymore, but instead you have these one-dimensional hydrogen chains, is due to the size of the metal atom. So if we calculate the chemical pressure maps, we see black around the calcium in this MH6 type structure, showing that the calcium is slightly too small for the hydrogen lattice. However, along the hydrogen-hydrogen bonds, we see that positive chemical pressure. So that means that the hydrogen lattice would like to expand. So you have this kind of balance of chemical pressures keeping the structure together, where the calcium is a little bit too small, but the hydrogens at the same time cannot expand further. So that is what keeps this structure together. For the strontium H6, on the other hand, we see the white around the strontians showing us the positive chemical pressure, so expansion would be favorable. However, within the hydrogen lattice, we see that it would like to contract. So essentially the inverse scheme of the calcium H6 chemical pressure maps. Now taking a look at the dimer, at the structure where you have undergone this structural transition to form these 1D chains, we see that there is no longer any chemical pressure along these hydrogen-hydrogen contacts where you do not have any bonding within them. And also the chemical pressure along this hydrogen-hydrogen chain has been relieved. And more so, within strontium itself, we do not have any sort of chemical pressures that are of large magnitude. They don't have positive CP in all directions, and just little bits of CP along this C-axis. So we've relieved the chemical pressure by undergoing this structural distortion.
Eva?
Am I out of time?
5 minutes.
5 minutes over or 5 more?
Yeah, okay.
5 more?
Over and more.
Okay.
Over and
more. Okay, great. No problem. Sorry. All right. So I'll just show you very quickly that another thing that one can do using this chemical pressure way of looking at the structures is to identify regions where you could put another stuffing atom. For example, if in the lanthanum H10 you take this atom out of the structure, what we note is that you would like to compress the tetrahedra, and you can do so by adding a boron to this tetrahedra, which relieves the chemical pressure in the system. Using this type of way of thinking, we have found that in yttrium H10, or you make this hypothetical yttrium H8, the yttrium is much smaller than the lanthanum. So instead, we can't just add a boron atom or another stuffing atom here. However, if we add a carbon atom, we are going to contract the carbon-hydrogen distances in making this CH4, thereby making the system stable down to about 50 gigapascals with an estimated TC of 60 Kelvin. Okay, and I won't talk about this, but we have also looked at MH4 type systems and studied the systematics of them, why some of them are superconducting and others are not. And it has to do basically with how the metal atom is going to affect the distance between these hydrogen atoms right here, and that has to do with its valence as well as its size. And it goes back to work that Roald Hoffman and Chaozhang Zhang did on studying this structure type in the BAL4 structure type. Okay, so I would like to thank the group members that have looked at this, in particular Xiaoyu Wang, Katie Hillicky, and Nisha Gang, my collaborators Russ Hemley, Ann Mall, Lami Nasha from UIC, and Tiyanga B from the Carnegie Institute, and to also thank my funders and to thank you for your attention.